Okay, this is our review of the upper sixth fields exam and specifically the multiple choice section. Okay, so we've got a satellite. Let's draw a little sketch of this. So we've got a satellite of mass m at a height r above a planet. So it looks like basically we're at 2r from the center of the planet. So our planet looks to be kind of shaped something like this. And then we're 2r from the center of the planet because it's a planet of radius r and we're a height r above the surface. Density is rho. So what's the force of gravitational attraction? Well, so typically F would be gmm over r squared. So r squared. Now in this case, this is going to be 2r squared, I think. 2r squared. Now, if we look at the options here, we can see that we're interested in the density of the planet. So we know that mass is density times volume, so we can substitute that in here. So we've got G, density times volume, m, over, and let's expand this now. So this is 4r squared. Now, the volume of the planet is given by 4 over 3 pi r cubed, m, over 4r squared. Okay, so now we just need to tidy this up a little bit. We can cancel some stuff out. We can cancel that 4 and that 4. We can cancel the r squared with 2 of those. And then that's basically going to be our final expression, isn't it? So it's going to be g rho pi r m, m over 3. So which one of those makes sense? G... The first one, isn't it? That is going to be A. So yeah, A is our correct answer for this one. Okay, a planet has a radius half Earth's radius and a mass quarter. Okay, so let's write an expression for the gravitational field strength on Earth. So this is G on Earth, is G m Earth over the radius of Earth squared. So that's our gravitational field strength equation. Now we have some other planet, G planet. And G planet has a quarter. So we've got 1/4 of ME. And then our radius is half. So we've got a half times the radius of Earth squared. Now, that is going to cancel out, isn't it? Because the half on the bottom, when it gets squared, is going to become a quarter. And so we're going to have a quarter on the top and a quarter on the bottom. So this is going to become GME over RE squared. And so therefore, it's going to be C, approximately 10 newtons per kilo, the same as the Earth. Okay, question 3. Radius of a planet is r, so sketch a little picture. So we have r. Gravitational potential at the surface, this is V equals minus 4,000 joules per kilo. What's the gravitational potential at a distance 2r from the center of the planet? Okay, so at this position right here. Okay, so the equation for potential, V equals minus gm over r. Or let's actually use a small r so that we're sort of saying more generally this is the equation. In the first case, it's 4,000. And then r is doubling. So what's going to happen to our potential? So when this, so let's see, so we've got minus gm over r, and then we want to, which is equal to 4,000 or minus 4,000. And then we're interested, what's the value of minus gm over 2r? Well, that's going to end up being minus 2,000, isn't it? It's going to be half as much. And so question 3, the answer is going to be B. Question 4. So we've got a 10 microcoulomb charge and then an uncharged conducting sphere. So what's the electric field lines? Well, we know field lines point from positive to negative. That's generally what happens with our electric field, points from positive to negative. So it needs to be pointing away from the center. So it's got to be B, C, or D. Let's think about what's going to happen on the inside of this sort of shell. So this shell here, let's kind of draw that out a little bit more. If there's a positive charge in the middle over here, so here's our positive charge, then all the negatives, because this is a conductor, are going to come here, leaving positives behind here. And so if we were to sketch the field lines, they'd go like out this way from positive to negative, and then out again from the other side from positive towards like some negative infinity, I guess. So C is going to be our correct answer for that one. Question 5. What's the acceleration of a particle and it's moving through an electric field? Okay, so acceleration is force divided by mass. We should say net force really, but I think there's only going to be one force here. The force on a charged particle is going to be QE over m. And E is equal to V over D. So this is going to be Q V over D over m. And tidy that up a little bit. Q V MD or DM MD. And so for question 5, A is going to be the right answer. Question 6. This is an annoying one, I guess. Electron, surface of the Earth. Oh, wait, is it? Oh, placed in an electric field strength. Okay, so what's the electric force? First of all, let's work out the electric force. This is Q times E. It's an electron, so it's 1.6 times 10 to the minus 19 multiplied by 5,000. So let's work that out. 1.6 e to the minus 19 over, times 5,000. 8 times 10 to the minus 16. And then for the gravitational force, this is going to be GMM over r squared. So the value of G is 6.67. I wish my iPad would stop doing that. 6.67 times 10 to the minus 11. Mass of the Earth, 5.97 times 10 to the 24. Mass of the electron, 9.1 times 10 to the minus 31. Distance between them is going to be the radius of the Earth, and this is one I can't remember off the top of my head. It's something like 6,000 or something like that. Hang on. Where's my data sheet? 6,000 kilometers, is it? Or 3,000? Earth, 6,000 kilometers, yeah. So it is 6.37 times 10 to the 6 squared. I said this is going to be an annoying one. It's just a long calculation, really, for 1 mark. And squared. 8.93 times 10 to the minus 30. 8.93 times 10 to the minus 30. And then we've got to divide these two by each other. So if I just label them quickly as like equation 1 and equation 2, we need to do 1 over 2. So what is that? 8 times 10 to the minus 16 over this answer. 8.96 times 10 to the 13, or D. Okay, next question. The electric potential at a distance r from a positive point charge is 45 volts. Okay, so sketch a picture will help me. So I have a positive charge here. And then the electric potential at some distance r is 45 volts. So V here is 45 volts. Potential increases to 50 volts when we decrease by 1.5 meters. Okay, so kind of if we decrease by 1.5 meters, then the potential here is going to be 50 volts. Okay, what is the value of R? Okay, so I'm going to write out some equations. So I know in the first case that V equals 45, which is equal to KQ over R. And I know in the second case, let's grab another color, I know in the second case that V equals 50 when this is equal to KQ over, what, R minus 1.5? Yeah, R minus 1.5. So from those, I can kind of combine those two equations together. Given that kq is a constant, in this case, kq is going to equal to 45r, which is going to equal to 50 into r minus 1.5. And now it's a case of solving for r. So 45r equals 50r minus, what's 50 times 1.5? 75, minus 75 right there. So 75, not 7.5. 75. So move things around. 75 equals 5r. R equals 75 over 5, which is 15. So 15 meters. Yeah, D is going to be our correct answer for question 7. Okay, next one, a unit for epsilon naught g. Right, so let's write out the equation for gravity. This is gmm over r squared. Let's write out an equation for the electric force. This is kqq over r squared. So, if we want to, oh, actually, we're not going to need k, are we? We're going to need 1 over 4 pi epsilon naught. 1, 4 pi epsilon naught. Okay, so, oof, what can we do here then? So, get g. G is fg times r squared over mm. So this is newtons meters squared over kilograms squared. I realize I want to maybe do something with that newtons in a minute, but I'm going to leave it there for now. Let's do this one over here then. Epsilon naught is going to equal to qq over 4 pi r squared fe. So this one is going to be Coulomb squared. 4 pi has no unit. Newtons meters squared. Okay. So we need to do epsilon naught g. So let's get another color. So epsilon naught g is going to be units, because that's what we're looking for, right? Yeah, units. Is going to be units of Coulomb squared over Newton meters squared. Hey, I'm glad I didn't change that Newton to something more complicated. Multiplied by g, which is Newton meters squared over kilograms squared, which is going to, I'm going to make these like equivalents, which is going to be Coulomb squared over kilograms squared. Is that an answer? Coulomb squared, kilogram squared. A is the correct answer for question 8. Question 9. 2 horizontal parallel plate conductors. I have to draw a picture. I love drawing pictures in physics. So these are separated by 5 mil, so 5 millimeters here. Lower plate is earthed. Okay, cool. So draw a little earth symbol. That's earthed. Lower plate is earthed. The potential of the upper plate is 50 volts. So this is 50 volts up here. Which line gives the electric field strength E and the potential the midpoint? Okay, so if we drew the field lines on, they're going to look something like this. It's a uniform field. So hopefully what you can remember is that the electric field is going to be constant. And it's going to be given by E equals V over D. So the voltage is 50, or the potential difference is 50, because the bottom plate, because it's earth, the bottom plate is at 0 volts. So potential difference is 50. The distance is 5 times 10 to the minus 3. So 50 over 5 times 10 to the minus 3 is 10,000 volts per meter. So that's fine. It's going to be downwards, isn't it? Hey, look at that. They're all 10,000. So it's got to be B or D, because the electric field is going to point downwards. So what's the potential halfway down? Well, if you imagine a particle at different positions, if the particle's up at the top here, it's got like its maximum energy, its electrical potential energy. If it's halfway down, it's got half of its electrical potential energy, and at the bottom, it's got no energy left. So it's going to be half, so it's going to be 25. So B is going to be our correct answer for question 9. And last one here, question 10. I nearly messed this up because I started doing Fleming's left-hand rule when I glanced at it. How does an electron move in a uniform field here? Well, an electron is a negatively charged particle, So it moves in, or it feels a force opposite to the field lines. Field lines are down, so it will feel a force upwards. And the only path which sort of represents a particle feeling a force upwards is going to be A. D looks like it's feeling a force to the left. C is feeling a force down. B is feeling a force to the right. A is feeling a force up. Force is up, which is opposite the field lines. So A is the correct answer. All right, I hope that was helpful, and I'll see you guys later.